Welcome to Modeling Mastery, the podcast where we explore the art and science of software design. I'm Hex.
And I'm Byte. In our journey through tactical design, we've assembled our toolkit. We have entities, value objects, services, events, and modules to organize them. We have all the parts, and we know how to structure them.
Now, in Chapter 10, we arrive at what is arguably the most important and challenging tactical pattern of them all, the aggregate. This is the pattern that brings many of the other building blocks together to form a transactional consistency boundary.
The aggregate is the answer to one of the most critical questions in domain modeling. How do we ensure that our business rules, our invariants, are always protected when we change a group of related objects?
This chapter is all about rules, heuristics, and design principles. We'll learn how to identify aggregate boundaries, the responsibilities of the aggregate root, and the rules that govern how aggregates can reference one another. Mastering this pattern is essential for creating a robust and reliable domain model.
It's a deep topic, so let's get started.
We now have our individual building blocks, entities, and value objects. But in any real domain, these objects don't live in isolation. They exist in clusters of close association. This brings us to a fundamental challenge. How do we protect our business rules across a whole group of related objects? This is the problem that the aggregate pattern solves.
It's a challenge that comes up everywhere. Let's use the e-commerce example from the book. You have an order entity, and it contains a collection of order line entities. A critical business rule might be the total cost of an order cannot exceed the customer's available credit limit. If your code allows a developer to load an order line directly from the database and change its quantity, how can you possibly enforce that credit limit rule?
You can't. The order line doesn't know the total cost, and it certainly doesn't know the customer's credit limit. If you allow direct access to the internal parts of a conceptual whole, you open the door for the system state to become corrupt and inconsistent.
And that is the exact purpose of an aggregate. An aggregate is a cluster of associated objects that we treat as a single unit for the purpose of state changes. The boundary of the aggregate defines a boundary of transactional consistency. Any change made to any object inside that boundary must be committed together in a single atomic transaction.
Within that cluster, one specific entity is designated as the aggregate root. This root is the sole entry point to the entire aggregate. It is the only object that anything outside the boundary is allowed to hold a reference to. All commands to modify any part of the aggregate, whether it's the root itself or one of its internal objects, must be sent to a method on the root.
The reason for this strict rule is that the aggregate root is responsible for enforcing the invariants of the entire cluster. An invariant is simply a business rule that must be true at the end of any successful transaction. In our e-commerce example, total order cost must be less than or equal to the customer's available credit limit is a critical invariant.
So, following the pattern, a client doesn't call a method directly on an order line object. Instead, it calls a method on the order aggregate root, like change line item quantity. The order root receives this command, finds the correct internal order line object, performs the change, recalculates the new total cost, and then checks if that new total violates the credit limit invariant. If the rule holds, the operation succeeds and the entire aggregate is saved in a single transaction. If the rule is violated, the root rejects the operation by throwing an exception and no state is changed at all. The aggregate root acts as the guardian of the boundary, ensuring that the cluster of objects it protects is always in a valid, consistent state.
In our last episode, we established the fundamental purpose of an aggregate, to act as a transactional consistency boundary, with the aggregate root serving as the sole gateway for all state changes. This is the first and most important rule of aggregate design. All commands must go through the root.
Now we need to discuss the second rule, which is arguably the one that causes the most debate and requires the biggest mental shift for developers. The rule is one aggregate can only reference another aggregate by its unique identity, not by holding a direct object reference.
This is a crucial and often counterintuitive point. So, an order aggregate should not have a private customer field. Instead, it should have a private customer ID field. Why is this distinction so important?
The main reason is to protect the consistency boundary we just established. If the order aggregate holds a direct reference to the customer aggregate, a developer could be tempted to write code like order.getCustomer.changeAddress. This bypasses the customer's own aggregate root, breaking its encapsulation and creating a backdoor to modify its state, potentially violating its invariants.
There's also a massive practical performance implication. If you allow direct object references between aggregates, what happens when you load one from the database? If an order holds a customer, which holds a loyalty program, which holds a tier level, you could end up eagerly loading a huge tangled graph of objects into memory just to perform one simple operation. It's a performance disaster waiting to happen.
It also creates enormous overlapping transactional boundaries. If you change a property on the referenced customer object through the order, does that mean you now have to save both the order and the customer in the same transaction? This is exactly the kind of large-scale consistency that aggregates are designed to prevent.
So the solution is to reference only by identity. The order aggregate holds a customer ID. But this raises a new question. What if a command on the order needs information from the customer to do its job? For example, applying a discount based on the customer's loyalty status.
That coordination logic belongs outside the aggregates. The responsibility falls to a client of the domain model, which is typically the application service. The application service would first use the customer repository to load the customer by its ID. Then it would load the order from its repository. Finally, it would call a method on the aggregate root passing in the necessary data from the customer, like order.applyDiscount.customer.getLoyaltyStatus. The aggregate root gets the information it needs, but it never holds a direct reference.
This design choice has profound architectural consequences. It naturally pushes the system towards a model that favors eventual consistency. By treating each aggregate as an autonomous unit that operates on information it's given, we accept that we can't guarantee that every object in the system is 100% consistent within the same transaction. The order applies a discount based on the customer status at that moment. If the customer status changes a millisecond later, that's a separate business concern, perhaps handled by another process triggered by a domain event.
Exactly. This rule, reference by identity, is not just a minor technical guideline. It's a core design principle that forces us to create small, autonomous aggregates with clean, explicit boundaries. It prevents performance nightmares, avoids large overlapping transactions, and guides us toward building more scalable and resilient systems.
We've now established the core rules for how to access and reference aggregates. There's one more rule about their life cycle, which is a direct consequence of the aggregate being a consistency boundary, and it has to do with deletion.
Right. The rule is simple. When you issue a delete command to an aggregate root, the entire cluster of objects within that boundary must be removed as a single atomic operation. You can't just delete the root and leave its internal entities orphaned. The repository's remove method should cascade the delete to the entire cluster, ensuring that the conceptual whole is removed all at once.
That rule is a straightforward consequence of the pattern. But now we come to what is perhaps the most important and often the most difficult heuristic for effective aggregate design. Keep your aggregates small.
This is where the art of modeling really comes into play. It's a natural tendency, especially when coming from a data modeling background, to create large clusters of objects that mirror the entire database schema. The book warns us that this leads to significant problems.
What kind of problems?
There are 3 big ones. First, performance. Every time you need to make a small change, you have to load the entire large aggregate graph into memory and then save the whole thing back. This is incredibly inefficient. Second, concurrency and scalability. The larger your aggregate, the more likely it is that multiple users or processes will need to make changes to different parts of it at the same time. This creates database locking and contention, which kills scalability.
Let's make that concrete with the Sazovation case study. The team initially modeled the product as a huge aggregate that contained a full collection of all its backlog items. A single product could have hundreds or thousands of backlog items.
And they felt the pain immediately. Every time they needed to plan a sprint or estimate a single backlog item, they had to load the entire product and its massive collection into memory. Worse, if one developer was adding a new backlog item to a product and another developer was trying to simply rename that same product, they were competing for a lock on the same product row in the database. The system couldn't handle concurrent users effectively.
So, how did they fix it?
They refactored their model by applying the heuristic to keep aggregates small. They realized that a product and a backlog item have different life cycles and, most importantly, different consistency requirements. So they split them. They made product its own aggregate and backlog item its own separate aggregate. Now, when you need to work with a backlog item, you load only that specific item. The change is small, fast, and highly concurrent.
This reveals the core guiding principle for designing aggregate boundaries. The aggregate should be just large enough to enforce its true invariants, and no larger. The only reason to group objects together into a single aggregate is if there's a business rule that demands they be 100% consistent in a single transaction.
Exactly. You have to constantly ask yourself, if I change this object, does another object have to change in the same atomic step to be valid? If the answer is no, if the other object can be updated later in an eventually consistent way, then they should not be in the same aggregate.
So the art of aggregate design is often a process of reduction. We start with our initial, often large ideas, and then we challenge them, always striving to find the smallest possible transactional boundaries that still protect the absolute must-have business rules of the model.
To conclude our deep dive into Chapter 10, let's bring all the principles of aggregate design together. We've established 4 core rules. First, protect the boundary by only allowing access through the aggregate root. Second, reference other aggregates only by their identity. Third, delete the entire cluster as one atomic operation. And fourth, the most important heuristic, keep them small.
With those rules as our guide, let's look at the practical life cycle of an aggregate. How are they created? Simply using a new keyword in a client can be problematic because it might not enforce all the necessary business rules to create a valid object from the start. This is where the factory pattern is essential.
A factory's job is to encapsulate the complexity of creating an aggregate. It ensures that when a new instance is born, it's in a completely valid state with all its invariants satisfied. This might be a standalone factory object, or it could be a factory method on another closely related aggregate root.
And once an aggregate exists, we need a way to save and retrieve it. This is the specific role of the repository. One of the most important rules of this pattern is that you only define a repository for an aggregate root. You would have a product repository and a backlog item repository, but you would never have a task repository because task is an internal entity within the backlog item aggregate.
The repository's contract is to manage the persistence of the entire consistency boundary. When you call backlog item.findById, it's responsible for pulling all of the data needed from the database and reconstituting the complete backlog item aggregate, including all its internal task objects. When you call save, it persists the entire cluster in a single atomic transaction.
Let's see how all these pieces come together in the backlog item aggregate from the book. Backlog item itself is the aggregate root. It contains internal child entities like task and discussion. It is the guardian of the invariants that span these objects, such as a task cannot be added if the discussion is not enabled.
All commands must go through methods on the backlog root, like add task. You can't get a reference to the internal collection of tasks and add to it directly. It references the other aggregates it's related to, product and sprint, strictly by their identities, product ID and sprint ID.
And by making backlog item its own aggregate, separate from product, its transactional boundary is kept small and focused. We're not loading the entire product just to add one task to one backlog item.
And that is the aggregate in practice. It's the cornerstone of tactical design. It's the pattern that takes our entities and value objects and groups them into a robust, self-validating, consistent unit that truly reflects the rules of the business.
Designing good aggregates is a challenging skill, but it's one that pays huge dividends. It requires a relentless focus on the true transactional invariants, not just on data relationships. Get your aggregate boundaries right, and you've built the foundation for a healthy, scalable, and reliable system.